Okay, good evening. What are we going to talk about? We're going to talk about a bunch of stuff this evening. I'm going to start with, in fact, this is a Codemotion webinar, and Codemotion is a conference I've spoken for before. I spoke, when was it? 2015 in Rome. That was a blast. And there's a few conferences coming up, Madrid and Milan. The theme is clearly the letter M. And you can go to the platform, codemotion.com, obviously getting stuff like this and stuff like that. And actually this evening, stuff like this. So what I want to talk about is the architecture of uncertainty. And this is an intentional, very intentional title. The intent, what we're looking at here is a lot of people focus on the idea of architecture being a thing that is certain. And so this idea of architecture and certainty is something I want to dispel. I want to focus on the idea of architecture being more adaptive than you'd expect. So I guess a bit about myself. So I co-authored a couple of books a few years ago on architecture, pattern-oriented software architecture. But I have a strong and very deep care for the detail. I edited this book, 97 Things Every Programmer Should Know, a number of years ago. But let's kind of look at this kind of question of what we're expecting. So Neil Gaiman, one of my favorite authors, had this little fragment in one of his books, one of his graphic novels, Sandman. And this character, Delirium, and she is the embodiment, she's kind of, as it were, the spirit or the being of delirium and deliriousness. And she says, what's the name of the word for things not being the same as always? You know, I'm sure there is one, isn't there? There must be a word for it. The thing that lets you know time is happening. Is there a word? That's a lovely way of putting it. How do you know time is happening? And this is clearly a deep and philosophical question, which we're going to answer very quickly, because her brother, Dream, is he's an entity of very few words, and he says change. Oh, I was afraid of that. And Delirium is expressing exactly the same problem that many software developers feel in the face of change. It's just like, if only there were not change, everything would be so easy. So if we're going to talk about architecture, I guess we need to have a definition. What do we mean by architecture? And there's this really nice definition that Grady Booch put forward about 15 years ago. Architecture represents the significant design decisions that shape the system, where significant is measured by cost of change. Now, this is an interesting definition for a number of reasons. It has a lot of implications. So the first implication is we're not just talking about structure. A lot of people think in terms of architecture being just purely some kind of structure. It's about load-bearing columns and stuff like that, like in a real building. And there's a truth to that, except that with software, we're dealing with stuff that's soft. When you look at a building, you tend to look at stuff that is big, and it's big in an obvious way. With software, it's not obvious what is big. And people tend to gravitate towards simple, perhaps an overly simple view that architecture is marketecture. It's the diagrams, it's the PowerPoint architecture, which is great and fine up to a point. But there's a lot of things in software that qualifies architectural without being big blocks. So, for example, what is the threading model of an application? And this is something that doesn't normally appear as a box. Boxes are about components in most people's senses. But threading is more fundamental, and sometimes people think of threading as like an add-on detail. It's just a little bit of extra about, you know, how the code runs. But let's just rewind. A little bit extra about how the code runs. It's how the code runs. It's actually effectively the laws of physics for your system, how things execute over time. This is fundamental, yet it doesn't get a place on the diagram. There are a few diagrams that represent threads as first class, but this just gets us away from the idea that it's just like the boxes. But it's very hard to change. If you've ever tried to change the execution model, whether it's threading, whether it's a time-driven system, however you have chosen, if you've gone from a system that is synchronous to a system that is asynchronous, all of these is changing the relationship of execution and time. And it turns out this is really hard. It doesn't really have a box, but it's incredibly hard. It is architectural. If you add exceptions to a language that doesn't have exceptions or doesn't use exceptions, as many C++ programmers experience in the past, and as a number of languages have done when they've added things like exceptions or threading over time, there's been a kind of a discontinuity. There's been a huge amount of effort invested in this, and a lot of mistakes and a lot of money. So what we're saying is that this qualifies as a significant design decision. It's significant because it takes a lot of effort to change it. And that effort may be represented in a box, but it's certainly more easily represented as either time or money or reversibility. So the idea is it's the big stuff. It's the stuff that's hard to move. It's the stuff that if somebody says, we're going to change this decision, now if you can fold it within a simple sprint, then it's probably not architectural, or possibly not architectural. But if it takes you longer than a sprint and multiple sprints, and you're changing something fundamental about the system and how it works, that's architectural. It takes a lot of effort. So there's another definition, which I think is quite useful. And that's Ralph Johnson's view, which is a kind of another way of looking at it. Architecture is the decisions you wish you could get right early in a project, but you're not necessarily more likely to get them right than any other, which is kind of a way of saying that if you only could reverse time. If you could reverse time, this would be great, because you go back and you say, look, honestly, I wish we had done this differently. I wish we had isolated the database more carefully. I wish we had chosen a different framework. Whatever it is, if you ever find yourself in that time travel moment, saying, oh, I wish we could go back in time and change this, there's a very good chance that what you're talking about is architectural. So let's look at a very simple way, a simple and intuitive, but sadly flawed way of reasoning about this, and try and understand where architecture fits in the life cycle. So let's try something fairly simple and naive. We're going to follow the course of the past, and sadly, as I've seen in a number of companies, the course of the present as well. What we're going to do is we're going to try and sit down and understand the problem. What is the thing we're trying to build? What is its purpose? What are the details of the domain? And we're going to call that analysis. Okay, so next thing we're going to say, we're going to try and figure out what it is that we're going to build. Let's figure out its shape and try and understand a number of the key decisions. And once we've done that, we're free to go ahead and actually develop it in detail, in code. And let's just be sure. Okay, we're going to test it. Now, that's great, but we may find that this doesn't go quite to plan. And there are a number of reasons why it doesn't go to plan. But normally people look at it and go, oh, we obviously didn't spend enough time trying to understand the problem. We didn't spend enough time designing. So let's reshape it. And this can become a dangerous cycle if you're not careful. Now, we know what really happens is that, you know, testing gets squeezed and squeezed, and actually we end up just saying, you know what, we'll let the customer test it, which is a polite way of saying we ran out of time. The other thing we're going to find is the coding phase does not last such a short time. Because during that, a lot of discoveries are made. Let's actually revisit what's going on here. What we're effectively saying is we're going to try and understand something without building it. We're going to try and understand something complex without building it. And then we're going to try and design it without developing it in detail. And it's complex. So we're going to assume the detail doesn't matter. And then we're going to hit the detail. which is when we're for a big surprise, because a lot of the problems that you discover, both large and small, are at this point of commitment to detail, the code. There's another thing that is interesting here, is that we are making a lot of big decisions. If you remember, if architecture is the significant design decisions, we're making a lot of them before we actually know very much about what's going on. We're making them in the first half of the development cycle, if we're going to partition the development cycle so tightly and tidily. So we're going to break this one down, and we're going to say, you're going to make the really big decisions, the decisions that are significant when you actually don't know very much. You know the most. Here's another way of thinking about it. When do you know the most? Based on the stuff on screen, you know the most when you finish testing. This is at that point you know the most about how you should have built it and what it is you should have built. And we're going to make all the big decisions early on. That doesn't sound very, well, very smart, very responsible. And there's so here's the challenge. Challenge is, it was highlighted by Edward Berard. I think this quote is from 1991. Walking on water and developing software from a specification are easy if both are frozen. There's this very simple idea that if we are able, it's a good thought experiment, if we're able to freeze everything, then there won't be any change. But change is normal. And there's a number of sources of change. There's an obvious one, which is the market changes. Unless you are about to develop something in a very short frame of time, so under a week, new product in under a week, probably the market's not going to shift much. The world is not going to shift much. The requirements of your customer, if you have a direct customer, that's not going to shift much. Your organization is probably not going to shift much. You know, don't forget, companies change. They coalesce, they acquire, they divide, teams change, you acquire, you know, you get new people on board, people move off. So these are the natural changes. So if you can isolate yourself from them, well done, but the chances are it means you're dealing with a very small piece of development, probably not a product development. It's going to be a short project rather than something that's going to span months and years and be an ongoing development. And that's the whole point, is that projects have an end state. The purpose of a project is to finish something. Products technically don't. The purpose of a product is to not finish, if you like. The goal of product development is to keep on playing, whereas the goal of project development is to play until you reach the finishing point. So they're actually opposed in a number of ways. So this is an interesting idea, because it assumes, it immediately questions the idea of we have a specification for a product. You have a first guess at something that will be a first or early release. But those are not the only sources of change. We may say, oh, customers always change their mind. Just replace the word customers with human beings, and you realize that the same applies to your technology stack. There's another thing that changes as well. And this you can run in a very simple thought experiment. So the thought experiment here is, just imagine that we froze everything. You know, the specification, the world, or rather, the team lineup, the technology. The specification is going to be complete. It's going to be everything you need to know. It's going to be comprehensible, and so therefore you can understand it, and it's never going to change. And yet, as you develop, you will discover something will change. First of all, the amount of software you have. It's called software development for a reason. So you will end up at the end of a certain amount of time with more software than you started with, but also your understanding. You will learn, you will understand more as time goes by. So here's the interesting thing. Even when you eliminate change, you can't eliminate change. And that tells us that perhaps we're using the wrong model to think about stuff. If architecture, the way that people view it is, architecture is you freeze things into place and they make everybody then follows a set of instructions. That's not even what architecture is for buildings. Certainly is not what it is for something as soft as software. So we need a little bit of help here to understand. Now, this is one of the, so Agile Software Development with Scrum by Ken Schwaber and Mike Beadle is probably one of the least read Scrum books. There's a lot of misunderstandings about Scrum. There's kind of Scrum as it was intended to be, and then Scrum, which is what people certify it to be. There's a number of interesting insights in this book, which was published in 2003, if I recall correctly. But one of them is the nature of the nature of Scrum as a process. And what do we mean by the nature? Well, Ken Schwaber, he specifically characterizes the different process models. The defined process control model requires every piece of work be completely understood. Given a well-defined set of inputs, the same outputs are generated every time. So defined processes are things like manufacturing processes. We know exactly what it is that we're after. And the goal is to recreate that given sets of raw materials and a plan for what is going to happen. And you get the same thing every time. And if you don't, then that is an error in manufacturing. So if you like, manufacturing is about the elimination of variation. You want to produce identical artifacts. Now that can be automated manufacturing, producing a car, for example, producing a phone, producing a pen. We want each one of these to be the same. It can also apply to human activities. So when if I go to a restaurant and I order a meal, if two of us order the same meal, we expect the same thing to be produced. But it's going to be produced logistically in the kitchen. We're expecting the elimination of variation. Yours should not look tastier than mine. If I go to a coffee shop and I order the same drink every day as I go in, then I'm expecting the same drink. It's the elimination of variation. And this sounds absolutely fantastic, except it sounds almost entirely unlike software development. Or, to be precise, we do have something that satisfies exactly the definition I've got on the screen. The defined process control model requires every piece of work to be completely understood. Completely understood, not like mostly, but completely. In other words, it has a clear definition that is semantically robust and framed well. Given a well-defined set of inputs, that's what we've just said, the same outputs are generated every time. We call this a compiler. That's what it is. It also applies to other automated processes, automated build systems, deployment systems, and so on. In other words, we're saying you understand everything so well that you can actually write an executable definition for it. That's great, but that's not the software development. That's the manufacturing bit. We solve the manufacturing bit. We've figured out how to produce identical artifacts. That's not a challenge. The bit that we have the problem with is what is the nature of the artifact we're producing? What is it that we want to build? How are we going to build it? What are the requirements? The requirements are a moving target. People don't walk around with a list of prioritized requirements in their head. That's a fantasy. That's just not how humans work. We mostly discover by discovery. We do it. We create it. In fact, if we're going to talk about agile development, the word agile itself originally comes from the Latin agere, which means to do. You've got to do it to find out. So what we're dealing with is something that is far more empirical. You've got to, if you want to find out what it is, you need to do it. You need to observe. You need to interact and experiment. So the empirical process control model expects the unexpected. It provides and exercises through frequent inspection and adaptation, control through frequent inspection and adaptation, processes that are imperfectly defined and generate unpredictable and unrepeatable results. Now, initially, when people look at that, they feel a bit uncomfortable because people don't want unpredictable and unrepeatable results. They don't want things to be imperfectly defined, but they are imperfectly defined. Even the most stable of projects, I read a number of years ago, sadly I can't offer you a citation, I've not been able to track it down again, but it was something like somebody had done a survey and they found that even the most stable projects and code bases still had a requirements change and drift and clarification of around 2% every month. That's actually quite a lot over a year. In other words, the things that are the most stable still move like rivers. So this idea that we are going to have an architecture that is the idea of our architecture is going to be frozen based on our somehow upfront knowledge. This is not how we're going to do it. We need an empirical approach. So when does design occur? Design occurs all the time. That's what we're saying. The idea is that design is not a thing that happens in a box early in the life cycle. Design is a thing that happens all the way through. You are always designing. But to give it a slightly more realistic view, there's another reason sometimes when we get attracted to kind of PowerPoint view of the world, all the boxes line up, all the arrows line up. Of course, we don't design and develop just incrementally like this. It's not just to iterate and go in circles. What we're really looking at is the idea of adaptation. We respond. You build something, oh, you understand it. Let's take a different direction. Let's continue more along that direction. You respond to the change that people are suggesting. You may find a particular architectural decision makes your life massively easier, that your whole list of potential performance improvements and opportunities, you don't need more. You just need a few at this point. Alternatively, you may make an early discovery that you actually want to take a very different course and investigate other possibilities. So if you want to build a good architecture, the fact that you're uncertain about something, the fact that you have options is a good thing. That you should be suspicious of people when they are certain. This is a rule for life. You know, politicians, if they sound certain, it probably means that they don't really know what they're talking about or they have an agenda. And I kind of feel a little bit the same way when people have a little bit too much faith in a particular set of technologies or approaches. There seems to be a kind of something missing. You want to hedge appropriately, because one of the things we know about software is change. Different processes, different networks, different markets, different frameworks. These all suggest to us that some of the things that we used to believe are not as true as they used to be. So therefore, you need to be accepting of that. So it's an active investigation. If you like, architecture is a conversation with time, and you need to be listening to have a conversation. So there's also another perspective which I think is interesting. We should look at another, sometimes it's interesting to look at other creative domains. One of the ones I'm quite interested in is writing fiction. And so there's a book by Robert McKee that is on the structure of screenwriting. Now, I'm personally not a screenwriter, but there's some interesting ideas in here, not all of which I agree with, but there are a couple of which I find quite useful. And it's a very curious little insight. He says, if a plot works out exactly as you first planned, you're not working loosely enough to give room to your imagination and instincts. That's an interesting way of looking at it. There's a suggestion here that you're being too tight, you're being too rigid, you're actually closing down your options rather than being open to them. The creativity requires the idea that a plan is a good start, but a plan is only there to give you a sense of familiarity, or well, a sense of the landscape. This is what I believe I know. But the more you know, the more it changes, and you should respond to that. There's also an interesting perspective here that if everything went exactly as planned, in one sense that's great, but in another sense there's a small amount of disappointment. It means that you didn't really learn anything, except that it went as planned. You didn't make discoveries that made things better, faster. In fact, this is an interesting idea when we start looking at that idea of unpredictable and unrepeatable. And software development should be unpredictable and unrepeatable, because when you do something that you are already familiar with, you won't do it the same way as you did before. You won't make the same mistakes. Well, we hope you won't make the same mistakes. There is an idea that you do it the first time, and there's a lot of learning. The next time you do something that is like it, hopefully you find new and more interesting mistakes to make. You don't repeat the same mistakes. You don't want it to be repeatable in that sense. It should take less time and involve more knowledge that you're able to bring on board. In other words, you drive it with your experience. In other words, we improve over time. And that's what you want from your architecture. Your architecture kind of starts out in one sense. Now, we can take this to an extreme. In fact, there's a nice gradient here. We're going to talk about writing. There's a page that I run on Facebook, Word Friday. And occasionally I will feature on a Friday an unusual word. And one such word is the word pantser, whose meaning really is not obvious. Pantser means it refers to a writer who writes by the seat of their pants. Now, this is wonderfully characterized by the author, Louis L'Amour, who was once asked by his daughter, why are you typing so fast? And he said, because I want to find out what happens. You don't know until you get there. You don't know until you've written the detail of the plot. You have to look at it in detail. And this is in contrast to a plotter. A pantser doesn't have a work to an outline. Now, I'm not suggesting the world is divided into plotters and pantsers. What I'm offering here is a gradient, or a spectral grid. That software development, a lot of software development lies along this range. There are things that we can plot out, and even plotters find that they need to pants occasionally because they find there is a twist that occurs to them once they're in the detail. All of which leads us to a conclusion that is not new. Jack Reeves, in What is Software Design, nearly 30 years ago, I think this was 1991, made the key observation that programming is a design activity. In other words, he's not saying it's separate. He's not saying there is design and then there is programming. He's saying it is a design activity. And this is characterized rather nicely in commit strip. Project manager talking to the developer. Someday we won't even need coders anymore. We'll be able to just write the specification and the program will write itself. And the developer says, oh, wow, you're right. We'll be able to write comprehensive and precise spec. Bam, we won't need programs anymore. Exactly. And do you know the industry term for a project specification that is comprehensive and precise enough to generate a program? Code. It's called code. That is what your code is. If you think that the code is instructing the machine, you may be disappointed when you learn a bit more about what machines do. Your code is so far removed from what's actually happening down there in the instruction pipelines and the caches that there is no resemblance. You would not be able to reconstruct your program just by looking at that. You're using a formal notation to define the design and the structure. There's a formal notation that has far more precise semantics than stuff that you deal with on a day-to-day basis, in other words, natural language. This is your, perhaps it goes into more detail than you might want, but it is an architecture definition language, although the problem is you're not able to separate out the things that are significant from those that are not as easily. So that one comes with time. That one requires a little bit of experimentation. So we've got this idea. If you describe something in enough detail that is unambiguous to be able to create a program, then you have programmed it. So what we're doing here is making it understanding. Code makes more sense more often than is believed. And the process of creating code will give you the feedback, the insights. You're pushing things into the detail and you're discovering what the detail is. You are challenging yourself to know the things that you might not otherwise have seen. Most of the problems that people encounter during code are not coding problems. They are discoveries about things that are deep and architectural. They are discoveries about technology choices. They are discoveries about requirements where we see little gaps or questions or even contradictions. These are discoveries. So they're not discoveries of code. They are discoveries during code. In other words, they are discoveries of other aspects of the system. Occasionally, of course, we do discover things that are code-related bugs or issues. But normally the code is so sharp and in focus that it's teaching us something else. And we need to recognize that. So the first guideline, if you want to be able to build, if you want to increase your certainty over time, you start from a position of uncertainty. If you want to find certainty, you need to build things all the way through, not just leave them as whiteboard detail. That said, I find a lot of developers lack the big picture because they only spend time in code and they never see the big picture. They don't see the architecture. They're never able to zoom out. So you need to work between both of these levels. And there's another aspect here. You can't just keep coding randomly, arbitrarily, or drawing pictures on whiteboards arbitrarily. Referring back to Neil Gaiman, you have to finish things. That's what you learn from. You learn by finishing things. So what we're seeing here is this role of learning and structuring knowledge is fundamental to what we mean by software development. And the structuring of knowledge is our software architecture. What we're saying is this is how we organize things. This is the relationship between these concepts. This is the distance that we want between these concepts. We want the close distance, says we want tight coupling. We want a deeper, longer distance. It tells us that we want a looser coupling, and we might want that for reasons of certainty, for reasons of uncertainty. Don't couple things that you're not sure about. You might want it for reasons of change that you know about. You might want it for reasons of separate execution. Testing is a brilliant example of that because testing gives you a different point of view. If you want to find out two ways of looking at something and you only have one piece of code, one piece of production code, fine, just test it. You have a second point of view immediately. So you can never know too much in this case. And why does this matter? Well, let's get back to this idea of the empirical approach. Tom Gilb's idea, his conceit, his approach to testing, architecture, is architecture is a hypothesis. Okay, it's not a fixed plan. It's a hypothesis. It's a belief. It's a testable belief. When somebody says we're going to do this because it's going to make things faster, or we should organize it this way because it'll be easier to maintain, they're making a statement that is perhaps a statement of belief, perhaps it's supported by experience, but it is a statement that could be false in the particular system you're working on. That's fine. There's absolutely nothing wrong with that, except failure to acknowledge that that's what you're doing. It's a hypothesis. It's not a fixed future. You could be wrong. Well, in which case you need to prove it. It's okay to have these ideas, but you need to explore them. Proven by implementation and measurement. Build it, measure it. Now, when we say measurement, immediately the attraction of that term is we're going to measure things like performance, runtime performance. And that's obviously relevant. If your architectural decisions are about performance, that runtime performance, that's perfect. But we're also, architecture is the structure of knowledge. It's where the developers live over time. If you're going to make that kind of statement, you can still test this. But your measurement is not over matters of seconds. Your measurements are over matters of sprints, okay, matters of weeks and months. If somebody says this is easier to maintain, okay, let's check back. You need to structure your development so that every few sprints, every few months you review. What were all those things that we said were easy to change? We made this decision because that was easy to change. Now we've run the experiment, let's actually look, is that true? And in most cases, you're going to find that either it has no difference or it's made things more complex, and occasionally it has actually made things easier to change. So the point there is that when we do, if you consider yourself an architect and you're not doing this, this is something to add and bring into your repertoire. If you're making statements, test them. How do you test them? What would show that that statement was true? And you can make observations on the version control. You can look for the hotspots, some code analytic techniques. You can look at defect density. If somebody says this technique will reduce bugs, don't just take them at their word, come back to it. We're very bad at going back to these decisions and revisiting them. And this is where we're going to get our certainty from, is by actually creating knowledge rather than just belief that is not, has not been falsified. And there's a kind of simple structure for this. It's an empirical life cycle, one of the oldest approaches in this sense, and it was captured rather nicely by Deming and Shewhart. Originally Shewart's work, I believe. Edward Deming characterized it in a number of different ways. Plan, do, study, act is the original characterization. You establish a hypothesis. This is what we believe. This is how it's going to go. Then you do the work. Then you stop. You study. Sometimes people call this plan, do, check, act. I'm not quite so keen on that terminology because the study aspect sounds slower. It sounds more cautious. Check sounds very quick. So what are you going to do with this knowledge that you have? What are you going to act on it? So there is this idea then of repeating the cycle. And this is how we establish, that's how we improve certainty. It is how we should be running the life cycle so that it supports the architecture. What are the things we're not yet sure of? What are the things we need to know? Well, let's try that. Here's a decision. This could be quite big. Okay, should we do that early? Should we do that later? What are our alternatives if that doesn't work out? Whereas often people offer it as a single roadmap with a single road. Now, if you have a roadmap with a single road, there's not a lot of point in having a map. The point of maps is they show you the possibilities, and you need to be aware of those. Now, this kind of starts looking a little bit disconcerting from an outside point of view, because it makes it look like we've lost track of architecture. This is a book on architecture, 101 Things I Learned in Architecture School. And what we'll actually find is if we actually bother to look at what building architects say instead of imagining what they say pretty much the same thing. Properly gaining control of the design process tends to feel like one is losing control of the design process. It becomes a little more meta. What you're doing is exploring. You are describing how you'll go about something. You're not saying that on this date this will happen. What you're doing is you're saying here are a series of unknowns, here are a series of risks. Here are the things that we need to target. We have a number of ideas, but I can't tell you exactly how it's going to work out, but here is our plan for finding out what our plan is. So how do people respond to this loss of control? How do they respond to this uncertainty? How do they respond to new discoveries? Because they weren't planning for them, they end up just, oh, well, this is a temporary workaround. And it's just like, yeah, right. Okay, I'll believe it when I see it. It does occasionally happen, but that's amongst highly disciplined teams who have a very clear idea. Who have a clear idea that if you say something is temporary, that's a statement. How do I know that that's going to be true? What is your plan for removing that feature? You've given me a plan for adding it, but what's your plan for removing it? People always talk about creating, adding new features or creating code. When is the bit where they remove it? Yeah, so in other words, how do we decommission this decision? How do we decommission this code? At what point does this code not become useful? Technically speaking, that's a really good approach. And it's a shame more people don't use it because they only think about adding lines of code. What is the exit condition for this code? So if you say this is temporary, how would I know that it's temporary? What's the exit condition for this? At what point will I know that this is gone? And what point will justify that? So we have the idea of a healthy life cycle life involves process. It involves discarding things. There is no life without some kind of death in this sense. There is constant change. And typically we centered this on the idea of refactoring. It doesn't mean things don't have to get old and worse. They can get old and good, and they can do that. The problem is, though, we often don't follow this carefully enough. We deal with uncertainty using the smell of speculative generality. Speculative generality, you get it when people say, oh, I think we need the ability to do this kind of thing someday, and thus want all sorts of hooks and special cases to handle things that aren't required. You speculate, you imagine all the possibilities. That's great, except that that's not going to work out very well because it's limited only by your imagination. If you have a good imagination, you're going to add an awful lot of general junk that's just not going to be useful. The trick is not to add these things. Speculation is a very powerful human faculty, and you can use this, but it's not to add stuff. It's mostly to actually keep stuff out. Sometimes people say, oh, well, we didn't add it in the code. We added it in the configuration. Yeah, well, that didn't work out too well either. Always remember, configuration is code. It uses a formal syntax. It affects the way that your code, the rest of your code executes. People have this idea, false distinction. They have their idea of we have code, we have tests, we have configuration, we have build scripts, and all the rest of it. It's all code. Just some of it happens to be production code. Some of it happens to be in one particular language, your language of choice, but some of it is in other languages. You may find that it is in a configuration language. It might not be Turing complete, but it shapes the way your application runs. It's a multiplier of complexity if you're not careful. It's a reducer of complexity if you're able to get this one right. How are you going to get it right? Experiment. Iterate and converge. So a number of years ago, there was a book, 97 Things Every Software Architect Should Know, and to this I contributed a couple of items. Simplicity before generality, use before reuse. And kind of a simple approach to this is to understand the best route to generality is through understanding known specific examples. In other words, look for the essence, look for what's actually there. Can you build it so that it solves a problem well? Keep your eye open for the generality, but don't overdo it. And then what you're going to do is discover the simplicity. Often we don't recognize how to simplify something until we have seen it, until we have experience of it, until we have learned. So this is the whole idea. The learning life cycle underpins this. You start from uncertainty, you move to greater certainty by actually doing stuff and reflecting back on what you've done, not always just sticking with the one decision because that's the architecture. The architecture needs to be a little more adaptive. Otherwise, if you're not a Java programmer, well done. You managed to miss java.util.date. It only took them 2 decades to get a decent date time handling facility. Java.util.date is possibly one of the worst pieces of single class design you're ever likely to encounter. The interface is riddled with guesswork and misunderstandings and kind of hope-based programming. But there's only one problem with it. Why couldn't they get rid of it? Well, they can't get rid of it because public APIs like diamonds are forever. Once you've committed something, it becomes significant. Or to be precise, once you've committed something to be published, it becomes significant. So there's an idea. Sometimes people think, oh, the only things that are significant are the big things. No, if I make a decision about using a 16-bit rather than a 32-bit integer, I have made a decision that is difficult to reverse the minute I publish it. And you might say, well, it's not a big decision. Yes, it is. It's huge. You try moving that decision. Once you have a number of other people, particularly people you're never going to meet in companies you're never going to know of, then suddenly you discover you can't change this. You know, it's no longer a question of changing the parameters on a refactoring menu. You can't go out and change other people's code like that. So the little things tend to multiply. So the first trick is don't publish what you're not sure of, or have a very clear model. This is the experimental thing. When you are publishing things, drip feed it to people. Don't give it all as one big bang release. Use your iterative structure to accumulate and say, this has gone from experimental to committed and dependable. You can now depend on this because we have been relying on, well, we've been experimenting with this. People have tried this, they've kicked it around, they've actually built real stuff with it, and we're prepared to make a commitment that this is how we want it to be in future. It's got to be an experimental thing. The minute you push something out, if that's the first time you've done that, you're filled with uncertainty. And how good are we at predicting the future? Always remember that this is one of those things. People love putting their company names and URLs in package names or product names inside the code. You don't control this. If you're a developer, you do not control the name of your company or the name of your product, except in a few small startup cases. Do not put the things that you don't control in your code. This is the Java package naming scheme was flawed from the moment it was introduced, and it's a shame that they went that way. It was well meant, but people get things wrong, and now everybody can see that there are packages called con.sun, and there's no sun anymore. Prediction is very difficult, especially about the future. We struggle to understand the past. We struggle to understand what is happening in the present. But if your architectural decisions are relying on you being able to predict the future, you're going to be in for a lot of very nasty surprises. Your architectural decisions should depend on you not knowing the future. Go into it saying, we have a bunch of ideas, we have a whole lot of experience, here's our proposals, or here's our hypotheses. This is how we're going to go about it. And you're going to understand when things are no longer practical or suitable because you're going to have exit conditions or decommissioning conditions, if you like. This decision is no longer applicable. Yeah? People don't think about the retirement of decisions or the retirement of code often enough. Now, if we're going to pick on architecture, and let's pick on building architecture again, if you're going to do it, then do it right. Lovely book, How Buildings Learn, by Stuart Brand, 1994. On the cover, it shows a pair of buildings. They were built in the mid-19th century. By the end of the 20th century, they had lost any similarity they had to one another because they'd adapted over time. Their owners, the different purposes to which they were put. And there is a very simple idea here, is that look at the rate of change. Look at the rate of change within your application. One of the greatest things that is overlooked in a legacy code base is a legacy code base has history. And history is a great predictor of the future. If you're not prepared to understand the past, expect to be surprised by the future. One of the things you can do is look at the things that change together. In a building, there are certain particularly functional buildings like offices, there are certain layers and structures that are more or less stable than one another. So that where a building is, the site is the most stable. The load-bearing structure is the next most stable, the skin, the exterior facade, following that. Then there's the services, the air conditioning, the lighting, the cabling, all of this kind of stuff. Then the space plan, and then the stuff, the chairs and tables within it. And the point is, you want a building to be sympathetic to this. You don't want it, if you want to move stuff around, and you want it to be easy to move stuff around. You don't want to put your services in the load-bearing structures, because it means every time you need to add a new service, such as cabling, or you need to update the air conditioning, it means you have to get access to the load-bearing structures. So the idea is you organize your building in sympathy with this rate of change. Now, software is far harder far more intricate and far more complex than this. But you have all of this code analytical data on how things change. And you can look, and if you can spot what are the things that change together, should you be depending on something that is more rapidly changing? Well, probably not. You probably need to isolate it through an interface or move the less stable things to appropriate packages or layers where they have in common with the other things their instability or their volatility. So there's this idea of treating our architecture as a more dynamic, more living thing. This is a response. It's a long-term maintenance role. It's not an injection at an early point in the life cycle. Of course, this is not news. This exact same insight comes to us for modularity, and it's no different in software. Everything is a module from something else, or to put it another way, we build large software systems out of smaller software systems. We build the smaller pieces of software out of smaller pieces still. So there is this kind of recursive structure, and David Parnas describes this. We propose that one begins with a list of difficult design decisions or design decisions which are likely to change. Each module is then designed to hide such a decision from the others. In other words, use your uncertainty to structure the system. So we've seen you can look to the past to see what has changed. You can look at defect density as well as history that we can get and use to inform future changes. But how do we deal with the future when we don't know? How do we deal with speculation without putting in too much complexity? Well, use your speculation to figure out what is likely to change. What are we not sure about? If we're not sure about something, don't depend on it. Don't couple to it tightly. Put some separation, either module, layer, package, whatever it is, separate from it. If you can come up with multiple alternatives, then that is also an indicator. In fact, there are cases where we can instantly predict where you're going to have instability or problems if you're not anticipating it. Alan Perlis's observation: if you have a procedure with 10 parameters, you probably miss some. Now, he's not saying you miss some in the call. What he's saying is, over time, you will discover that 10 is as good as 11. You missed an 11th, then you missed a 12th, then you missed a... In other words, this is not a cohesive grouping. You're always going to remember something else, and then there's another thing, and then there's another thing. But we can also use other indicators, and this idea of marking out the uncertainty, that idea where we can see alternatives. And this is sometimes an interesting social challenge and brings out one of the other social aspects of architecture. So using uncertainty as a driver, this is a contribution that I made to 97 Things Every Software Architect Should Know. When a design decision can reasonably go one of two ways, an architect needs to take a step back. The temptation is that you have two people with option A and option B, and one person's trying to convince the other that this is the better option, and this person's trying to convince the other that it's better, and this becomes the problem. Instead of trying to decide between options A and B, the question becomes, or should become, how do I design so that the choice between A and B is less significant? In other words, let us say we go with this one. What happens if in 6 months' time this proves more suitable? Either because this was never a good idea, or more commonly, this was a good idea, but the world has changed. We need to move to this one. In other words, we've reached the exit condition for this. Something in our architecture, something in our customer, in the market has changed. Something in our technology base has changed to make one decision better than the other. It's changed. Good is a function of time. It's not fixed at one point. So, in other words, these are both potentially good. What could I do to keep the distance between away from over coupling so that I end up having to do masses of work to migrate from option A to option B? How do I reduce that? So the most interesting thing is not actually the choice, but the fact there is a choice. So on that, I will end with Voltaire's observation that uncertainty is an uncomfortable position, but certainty is an absurd one. Okay, so I hope that's been interesting and has now perhaps made you more certain of uncertainty. But if you've got any questions, let's see if there are any questions kicking around. Let's have a look. Okay, yeah, we've got some questions, and now I just need to figure out how to. Okay, so yeah, so there's an interesting question, observation. How do you deal with having less experienced developers on your team, making the things learned about the architecture while programming extremely variable? That is, people don't learn equally. This is very true. And this is an important point. Other people can't learn something for you. You cannot know something else on behalf of somebody. If programming is designing, how do you make sure the experienced people are doing the designing? Well, let's change this around a little bit. Let's try and mess about with it a little bit. So, how do you become more experienced? That's the first question. Well, one of the things you need to do is participate. An architecture. Well, let's use the building metaphor again. A building is not simply a structure. It's not simply a bunch of load-bearing walls and spaces. It is actually designed to accommodate a particular activity. So a home is designed to accommodate a family or a group of people living together who are either sharing in some way. They're sharing space, they're getting on with their everyday lives. That's the basic idea there. An office has a different purpose. A hotel has a different purpose. Each one of these buildings has something about it that meets that purpose. So school, its organization of spaces is fundamentally different to that of a hospital. So they accommodate an activity. So let's look at it this way. A code base is surrounded by its development practices as well, and it's also its tooling. And when we talk about development practices, how do new people become more experienced? How do the less experienced become more experienced? It's a model of participation. What you're trying to do is say, this is how the architecture gets learned by other people. So how does it get learned? Well, you could send a few people off and say, here's the documentation, go read this, and go off in the corner. Or you sit with them. You could say, we will review the code separately on every pull request, and somebody else will give you feedback, or you can sit with them. You kind of see where I'm going with this. Software development is a social activity. All these things that separate us are not turn out to be, they don't save us time, they cause us problems. If you want people to work together, then they actually need to work together. So the trick here is to get people together, the experienced and the less experienced. That's how you do it. There is also a dangerous assumption, and this is kind of highlighted here, and I want to point this one out. In programming design, how do you make sure the experienced people are doing the designing? I absolutely don't want, I want to ensure the experienced people are not the only people designing, because the worst thing is when people think they have, because they have experience, they have confidence. And I mentioned earlier, that's a real problem. What you want is the people that don't know things to ask questions. You want the people who have new ideas to be able to participate. If only the experienced are participating, then what you're going to end up with is an architecture that looks like that. It's going to be potentially very narrow unless you have a good social structure. So really, let's put it another way. How do I get it so that everybody is as smart as they could possibly be? And that's a social question. So therefore, this idea of keeping developers separate and keeping our activities, I review on I review on pull requests and stuff like that. This is a terrible way of doing it. I mean, it's better than not doing reviewing, but if you actually want to share stuff and you want people to learn, then you actually need to do this stuff together, whether that is through pairing, whether that is through whiteboard and projector sessions in a meeting room. That's what you want. You don't want people sitting there typing the wrong thing, typing lots of it. That's often the way that people optimize development. Let's have people typing faster. Typing is not the problem. So my answer to you, Noah, is very much recognize the social dimension. Everybody's going to, exactly as you observe, everybody's going to learn differently, but we cannot assume that because people are more experienced, they will have the right insights. Experience is not linear. It's not a thing that you just go up. you have people with different experience. It turns out that you can have two people with the same experience or the same amount of experience if we can quantify it, but actually it turns out their experiences are fundamentally different. They've seen different things. They have different approaches. You want to make the most of this group intelligence rather than the least of it, which is unfortunately the way we often structure teams. A question from Mike here. Good advice on publishing APIs. Can you tell us something about becoming dependent on the APIs of others? If you can't predict the future of your own project, how can you anticipate if that's a useful dependency? That's a really good question, and it touches on something else that is not, to which obviously there isn't an easy answer. I've had similar questions before when somebody said, well, you know, we depend on an API from Amazon or whoever, and that API has now been retired. Our whole product depends on that. What do you suggest doing? I suggest getting a time machine. You're screwed unless you're able to work around it, or you already have a diverse portfolio of products or whatever. So here's the thought. I'm not sure I can give you an exact answer that doesn't involve a time machine. What I can do is I can say, start experimenting. Find out what your dependencies are. People are very casual about dependencies. What is a dependency? A dependency is a risk. Simple as that. What are all the things that you depend on? What is their volatility? What is the risk to you? What is your level of control? If I write a piece of code and I give it to you and we're on the same team, then you're depending on that code, and actually it's our code, so that's great. So it's not my code, it's our code. We have a dependency on our own code, that's fine. We control our own code, that is also fine. This code is based on a framework from somebody else. Do we control them? No, probably not, unless it's in-house. So we may get a convenience, but there's also a risk. What if they continue not to develop it? Well, the risk there is that we never get updates and we're stuck with a particular view of the world. It could be worse. If it's something that involves security and we're never getting updates, that is genuinely worse. You depend on your programming language, you depend on your platform, you depend on the network. What happens, how does your product fare if the network goes down? Yeah, not so well. Okay, so in other words, you may not be able to address all of these risks, but if you certainly won't be able to address them if you don't enumerate them. Everywhere you have a dependency, you depend on a number of things. Connectivity, you depend on other people's databases, other people's APIs. And this idea that we just reuse any random thing off the internet, that's a terrible thing, because what you've just done is you've increased the risk, you've increased the attack surface area. Be a little more cautious. I'm not saying don't reuse, I'm not absolutely saying that. We do want to do that, but you need to understand when this depends on this, what is the nature of that dependency, what is the nature of control, and what is the consequence of this going going south. If the network goes down, then I'm going to guess everybody's going to share the same bad experience of not only our application, but everybody else's application. And that is, we hope, temporary. If a company goes out of business or they retire an API and your whole product is founded on that, that's a little more, that's business critical rather than a matter of inconvenience. So the first thing to do, go through, find out what are you depending on. Is it find out what you gain from it over time, and if there's anything else in that space. If somebody says, look, there's loads of things in this space, so if we change our mind, we can migrate from one thing to another. That mitigates the risk. But if everything depends on one thing, you are a value add to another site, and that site changes its APIs, not just upgrades them, modifies them, but withdraws them, then that is a criticality that you need to acknowledge, but you can't necessarily control. And another question from Mike, which I think is an interesting one. How useful are architectural reviews done by architects completely detached from development? Less useful than if they were attached to development, I think. I'm not going to say it's not useful. I think another pair of eyes can be very helpful. And often when people, not simply architects, but if people come to review a product, if they come to review a code base, they come to review the architecture, the team practices, if they don't know something about them, that can actually be used to their advantage. And it's a little bit like the less experienced versus more experienced person. The person who's less experienced perhaps has fewer preconceptions. They are perhaps more ignorant. You can use ignorance constructively, just as you can use uncertainty constructively. The very fact that somebody doesn't know something gives them the ability to ask things. Sometimes they're really obvious things. Sometimes they see the oversights, or get you to explain something that on explanation, okay, what? Now I think about it, that wasn't quite as smart as it could have been. So there is a benefit to having a review done by somebody who is not involved and is relatively ignorant, because they will see something that nobody else will see. At the same time, that can't be your only form of review. There's another question of how is the review done? I don't want to say all reviews are good or all reviews are bad. I think reviewing as a general improvement of a social side and the bringing of more intelligence to the table is a great thing, but how is it done? If some people feel uncertain or cautious about reviews, there's a very good reason for that. Not all reviews are done in an objective fashion. Sometimes people feel that they're having to be a little defensive about their work. So we need to be very careful how the review is done. So in that sense, when we say, does it matter who does the review? The answer is yes, and it's not necessarily by whether or not they're an architect or how close they are to the project, but actually by how good they are at reviewing and being able to offer constructive review. This is a really important idea. What are the areas for improvement? What are the areas that are stable and good, and practices you should roll out across the rest of the code base and across the rest of the developers? So another question from Colin here. How do you address high-level refactoring in a reactive, fast-paced environment when stopping and rethinking the whole architecture is not a plan? Will it create more chaos if you just try to do it on the go? Oh, that's a good question. Do we stop the engine in order to change the engine? So let's go back to the roadmap example I mentioned earlier. The idea is that you don't just come up with an architecture roadmap once, and you don't just come up with a single road. What you should constantly, if you get this, if you drive around with Google Maps, you get a number of alternative routes, similar ETA, or this one's 6 minutes slower. Do you want to take this one? It's 2 minutes faster. In other words, it's constantly being updated. Now, the reason I say that that's relevant is because if we're going to talk about fast-paced environments that are reactive, then it means that if you have a notion, what we're doing here is we're actually planning. Sometimes people think plan is a dirty word. I don't have a problem with it. It's just that the fact that planning is a continuous activity, as it's suggested, planning. And a plan is simply a snapshot. This is our current understanding. But we're going to go a step further. We're going to say, here are the outcomes of this plan. You're not going to say there's a single outcome. There's a number of possibilities. Which one of these looks good at the moment? Now, when you've got that allows you to make these decisions. Okay, maybe we want to re-architect, refactor in that direction. So in other words, if there's something you're saying, look, this piece of code here, it's a legacy lodestone. It's a weight around our necks. We need to do something with it. But it's also where a lot of the business value is. How are we going to tackle that? Well, first of all, let us assume that we can't just turn everything off and say, right, stop everything. We're going to have to keep this one running. Okay, what can we do? Well, what could it look like? And this is an interesting exercise. I've done this with a couple of teams where what I've said is, imagine yourself 12 months from now or 18 months from now or something. What could this look like? Yeah, make it practical. Don't give me your best fantasy of what it could be. Tell me what you could do, what you believe you could do in 12 months' time. And then you kind of do a rolling wave back towards yourself. So in 12 months, it could look like this. In 6 months, it could look like this. In 3 months, in 1 month. Look at it like that. Now, normally when people get down to 1 month, they say, well, we can't do those changes. That's too much. Or this month is special because we've got a big release, or this month is special because there's a public holiday, or whatever it is. Every month is like that. There's nothing new. So now what you do is you say, what could we do in 1 month? Now roll it forward again, 1, 3, 6, 12. So in other words, this is where we're heading. Get yourself a practical direction of where you're heading. And every time you're making changes in such a fast-paced environment, every time you're making those changes, are they
Are they in that direction? Are you moving in that direction? Have you nudged the whole thing in that direction? Otherwise, you end up with this idea of like, we'll just keep doing what we're doing, and then one day magic will occur and we'll teleport from A to B, and that's never going to happen. So there's this idea of understanding what you can do that is sympathetic to these alternative directions. But unless you outline them, it's unlikely you'll accidentally stumble across them. So therefore, you have to be just as fast-paced. Your vision of the future has to be adaptive. You have to say, here are 2 or 3 possible futures, and here are some roads that might get us there, and that could change with time. And there we have it. And thank you, Noah, for your feedback. So I hope that's been useful and insightful. If you have any other thoughts, I'm easy to find online, the benefits of having an internet unique name. But failing that, I guess my Twitter handle is fairly easy to find, and most variations of me are easy to find, so Kevlin Henney, and I hope to see you online sometime. Thank you very much.